Let me start by thanking the organizers of this workshop for taking the initiative to honor Dr. Srinivasan in this manner. He was one of the most respected members in the community for his knowledge, his contribution, and also his personality. I had contacted both Dr. Srinivasan and Jean-Paul Babirian last July 6th about the possibility of collaboration. Dr. Srinivasan replied the next day and sent a copy to the professors at ITTK, who are the organizers of this workshop, suggesting that I contact them. We were all saddened when we learned a few weeks later of his passing. We are honored to make this presentation in his memory and also to honor the legacy that he left for us. The title of this presentation is the Lattice Energy Converter. You might ask, what is a lattice energy converter? Well, a LEC will spontaneously initiate the production of ionizing radiation and electricity based only on the thermal energy in its lattice, such as palladium that is polluted with hydrogen or deuterium. A LEC will produce sustained ionizing radiation and electrical energy when the lattice material is in fluidic contact with a gas or vapor containing hydrogen or deuterium. A LEC does not require naturally radioactive materials. It is mechanically simple to construct, but understanding the physics is very complex, and it's also easy to replicate. Those were some pretty bold claims that I was making about the LEC, and there's a statement that extraordinary claims require extraordinary evidence. So here's some of that evidence. A photograph of a LEC attached only to a digital voltmeter, reading 109.8 millivolts. It is spontaneous, self-sustained electrical energy, and it's been doing this for several months. The DVM has a 10 megohm input impedance. Here's another LEC. The difference being in this one that we used a galvanized pipe instead of a brass pipe. The primary reason for doing that is galvanized pipe or zinc has a different work function than brass. For this test, you see that we were producing 73 millivolts through a 1 megohm impedance, and the pressure in the cell in this case was about -8 inches of mercury, and it has also been operating for several months. This slide shows a cutaway view of a LEC. As you can see, it's pretty simple. In fact, virtually everything can be purchased at your local hardware store, starting with an 1/8 inch by 4 inch brass nipple, which is threaded at one end with a 5/16 24 tap, and then co-deposited with PDH or PDD. This becomes the working electrode. The 5/16 24 set screw is screwed into the newly threaded nipple, and this becomes a contact between the working electrode and the outside of the LEC. The 3/8 inch by 5.5 inch brass or galvanized pipe nipple becomes the counter electrode. Bushings at either end of this nipple go from 3/4 inch to 1/4 inch and allow for the connection of a valve at one end to evacuate and fill the LEC with hydrogen or deuterium. At the other end, the nipple has a high temperature epoxy fill with the wire passing through to provide electrical insulation and also seal the inside of the LEC. Small high temperature O-rings or a bead of high temperature epoxy is used to maintain the separation distance between the working electrode and the counter electrodes while allowing the gas to pass between. One of the first questions that people ask is, has anyone else replicated our results? The answer is yes. In this replication, Jean-Paul Babirian used a 2 millimeter diameter palladium silver alloy, about 4 inches long, as the inner working electrode. He put it in a cell, filled the cell with hydrogen gas, and heated it to several hundred degrees C in order to increase diffusion of hydrogen into the metal lattice. Unfortunately, his first attempt did not work. He contacted me, and I suggested that he co-deposit a layer of palladium onto the palladium silver rod. He did that, and 2 days later I got an email from him with the subject line, "Success." He had reassembled the cell, filled it with hydrogen, and it started producing 300 millivolts. Then, after a little bit of alcohol vapor got into the cell, it went up to 500 millivolts. Just a few days ago, John Paul Bavarian reported some new results. Whereas his first cell had been fairly small, this one was much larger. It consisted of two concentric cylinders, approximately 10 centimeters in length, where the outer cylinder was a silver foil 6 centimeters in diameter. The inner cylinder was stainless steel, approximately 5.6 centimeters in diameter, resulting in a 2 millimeter gap between the cylinders. Palladium had been co-deposited on the inner surface of the outer diameter cylinder. When he assembled the cell and pulled a vacuum, no voltage was measured. He filled the cell with hydrogen gas and started producing 540 millivolts. After several hours, the voltage had risen to 740 millivolts through a 10 megohm load. He conducted an additional load test, and as you can see, as the resistance went down or the load went up, the voltage dropped, but this was still a pretty robust performance from this cell, and this was all at room temperature, so we're anxious to see the results when he increases the temperature. The other interesting thing is when we compared this with some of our smaller cells, they scale about the same way, so it looks like what we're doing or the performance of the LEC will scale. A few weeks after the initial replication by Jean Paul, Andrew Erickson replicated on November 23rd of 2020. Andrew is one of the senior leaders at Los Alamos National Laboratory. Although this work was not done as part of the laboratory, he did this at his home. He started with the 1/8" nipple, which he co-deposited, and then put it inside a 3/8" brass nipple. Notice that he has cut a window into the brass nipple because he hopes to be able to identify some of the ionizing radiation with sensors he has. When he did this, the cell produced 115 millivolts into a 5 megohm load in air. It increased to 170 millivolts when hot air was blown into the cell. We have observed similar things when our experiments where air is sufficient for the cell to produce a sustaining ionization at a low level because there is some hydrogen in air. Future replications, as I mentioned, we are collaborating with the Indian Institute of Technology in Kanpur to conduct replications with additional instrumentation, and they're held up now by access to the campus and probably graduate students. Another replication, my grandson, 8th grade, was planning a replication as a science fair project, but the science fair was canceled due to COVID, so maybe next year. The pathway to a LEC started over 150 years ago when Graham showed that palladium metal occludes hydrogen. In 1896, Thomson and Rutherford showed that the conduction of electricity in gas is due to ions. And in 1928, Kramer showed that ionized gas between electrodes of dissimilar work functions produces a voltage and current through an attached resistance. In 1989, Pons and Flashman showed that deuterium and palladium releases energy during electrolysis. Since that time, Leonard scientists have reported that output increases approximately exponentially with temperature. Also, I want to note at this point some papers that are in the LENR-CNR library by Rout, Srinivasan, and others in the early 1990s reporting that ionizing radiation was being produced. And I'll have more to say about that later. We didn't set out to build a lattice energy converter. In fact, what we really wanted to do initially was to see if we can conduct high temperature gas electrolysis so that we could increase the temperature of the palladium cathode higher than what you could do with a liquid electrolyte. We knew that to have gas electrolysis you had to have ions in the cell, so for some of the cells we put americium sources in the cell to ionize the gas. You can see the instrumentation that we had a high voltage supply that had a current limiting resistor, 1 megohm current limiting resistor, so that if for safety purposes, if we got across the cell, we would get a little tingle rather than a big jolt. And the instrumentation was conducted by a LabJack instrumentation system, which has up to 14 channels of data that you can record. Here's a sample, a screenshot, showing what the LabJack data looks like. The LabJack's data is on the right, and you can see on the bottom the data scrolling across. One of the things you'll notice is that there are a lot of activity. There's a lot of activity a very short, less than 1 or 2 millisecond bursts of energy. These kinds of things that you would not see in a calorimeter. On the upper left, you can see the data that has been processed, and below that is the files that are being stored. When you're saving data, 14 channels of data at 512 samples a second, you generate about 8.5 megabytes of data per minute. So what we do is every minute we close out a file and process that data in real time so we don't end up behind in our data processing. Here's another picture that shows some of the spikes and also some excursions where the cell jumps up considerably and then goes back down. But even some of those excursions you would not see if you averaged a calorimeter over several seconds in time. As I mentioned, when we were conducting these tests, we knew that we had to have ions in the gas if we were going to have any conduction. So we spiked the gas with 6 microcurie sources of americium-241, hoping that that would produce enough ionization that we could then produce fugacity and load hydrogen into the working electrode. During the test, we realized that the current we were conducting in the cell was several orders of magnitude greater than what we would have expected with the americium-241. So we took a test where we removed the palladium hydrogen cathode and replaced it just with a blank copper tube. At that point, we could not detect any ionization. The americium-241 was not producing enough ions. Then we took the cell where we had emptied the americium-241 and had only the palladium hydrogen cathode in there, and the cell conducted. So the conclusion was that the palladium hydrogen was ionizing the gas. Here's an example of what happened during those tests when we were conducting the experiments. You see, we'd start out and they were all different. Every one was different, but this one started out very low current for a few days. One spike that perhaps lasted a few milliseconds or maybe even a minute. And then at point A, it jumped up to about close to 700 microamps of current. That continued. At point B, we did a low test. I'll say a little more about that later. At point C, for some unknown reason, it dropped down. At point D, it went back up and then dropped down. At point E, it went back up and stayed up for a day and a half or 2 days, at which point we just realized that the current limiting resistor that we had in the circuit was limiting the maximum amount of current that we could measure through the cell. So we changed the electronics, changed the resistance so that we could conduct twice the current. And when we did that at point F, it jumped up to over 1200 microamps. We thought it lasted there for a day or two. We thought, well, if a little is good, more is better. So we tried that gambit again. This time it went up for a short period of time, a few milliseconds, and then dropped. So whatever had happened, we had burned out the cell or something, and the cell never came back, at least during this time period. I mentioned that at point B, we did a variable load test, and I've got some data on what that is. This slide shows the test that was conducted at point B on the previous slide. In one of these tests, what we would do is we would reduce the voltage in steps of typically 50 volts or so, and monitor the current as it comes down. And so here you see the voltage is on the lower trace, the current is coming down on the upper trace, and then we go back up and the voltage, everything responds pretty nicely. Down below is a plot of voltage, current versus voltage, and you see the one of those plots is coming down and the other plot is going up. We knew that relative humidity would also affect the conduction of gas based on some work that Carlin had done around 1980. We developed a plot of that around the temperature ranges we were using, and you could see that it was going up by several orders of magnitude. However, when we did our experiments, we were at least 3 orders of magnitude more conductive than what the relative humidity could account for. As another test to see if we're getting any relative humidity, we put the cell in some dry ice that took the temperature down to minus 55 degrees C. At that point, there should not have been any water vapor in the gas. And we conducted the test, and you see the plots are very similar to the ones that you saw previously. And down below, you see the plot also down there, the voltage or current versus voltage on the lower trace. Here's another plot of data. This is a semi-log plot of current versus voltage. And you see it was coming down at a nice, relatively straight line until it got to lower voltage, about 25 volts, and then it dropped precipitously. At the time, we thought, well, that was just our instrumentation. It was a roll-off that was associated with that. Later, we realized that no, there was something really going on there. Here's a plot of data where we took the cube root of the current and the cube root of the third order polynomial equation versus voltage. And you see they line up pretty close together. The important thing to note here, however, is that this curve does not go to zero when we have 0 volts. That was surprising to us. But that would be easy to check. All we had to do was turn off all the power and unplug everything, which is what we did. And that's where you see the first picture that I showed. We had the LEC. All you need for instrumentation is a voltmeter, a variable resistance box, and a thermometer. Characterizing the LEC involves measuring the spontaneous LEC voltage across the load and resistance as a function of both time and temperature. At selected temperatures, vary the load resistance and calculate the current versus resistance. We postulated physical and electrical processes that could produce the experimentally measured values, and again, this is where studying the work of Thomson and others was important. We believe lattice vacancies as a function of temperature, and that could be important. Conduction of electricity through gas as a function of electric field strength in the gas. We don't have that much electric field strength in the gas, and yet we still conduct a lot. Conduct as a phenomenological equivalent circuit, and I'll show you one that we came up with. Refine the equivalent circuit using different LEC configurations and different measurements, and then refine the LEC design to optimize the production of current. So far, we've designed and tested over 100 different LECs. They include cylindrical air-filled open cell, where we did LEC voltage versus time, cylindrical hydrogen or deuterium-filled closed cells with both about the 1.1 millimeter and the 6 millimeters electrode separations, LEC voltage versus temperature at fixed load resistance, LEC voltage versus variable load resistance at fixed temperatures, cell current and impressed voltage versus time at variable temperatures, cylindrical hydrogen-filled closed cell with a split counter electrode, LEC voltages between the two counter electrodes, and cylindrical deuterium-filled closed cell with radial electrode structure of copper and zinc fins with a separation distance up to about 4 centimeters. I'll say something more about this and show some figures here, but basically what we were trying to do here was do the contact potential difference measurements if we were ionizing the gas, and we could measure LEC voltage between the fins. This illustrates the data collected on a typical test. You see, we were heating the cell over time, and it took several hours of heating the cell up, and the temperature went from roughly room temperature up to a couple hundred degrees, 180 degrees or so. And over that time period, you can see how the conduction of the cell, how much keeps going up, and it goes up monotonically, but very fast at first. This slide shows a typical test to characterize the LEC. In this case, we're measuring cell voltage versus load resistance across time. We had a resistor box, and by changing the resistance values, we could change the load on the LEC. And as we changed the load, we could watch the current come down. And as you can see here, we started at about 1 megohm, and we ended at probably less than 50 ohms across the cell. Then we went back to 1 megohm, and the voltage went back to the previous example. This slide shows the elect voltage and current at 3 different temperatures during a load test. You see the temperatures were 80 degrees C, 140 degrees C, and 185 degrees C. At each of these temperatures we would do a load test, and then using Ohm's law we could calculate the current, which we plotted down below. So what you see is the current is fairly constant until you get up to the higher resistance levels, at which point it drops off. So the question is, where does the current going as it drops off? This is one of the cases where Thomson was able to help us because he described a shunt load current in the cell. As you get more and more ions in the cell, some of them will migrate through from one side of the cell to the other, as opposed to going out and through a load. And in fact, Thomson says it should be a straight line. By plotting the difference in temperatures, in this case happens to be for 185 degrees C, you see we get a straight line. So this plot shows the total current, where we have the radiation current, the load is equal to the load current plus the shunt current. So now we have the I load, the radiation, and the shunt it comes up as the load current goes down. Now I mentioned that this is 10 to the minus fifth amps of current, 10 to the minus fifth amps of current, which isn't very much, but it's equivalent to 6 times 10 to the 13th becquerel. Recall that 1 curie is 3.7 times 10 to the 10th becquerel, so we've got 3 orders of magnitude more current here, more ions being moved, than what 1 curie of radioactive material will provide. So interpretation of the load current versus the load voltage and resistance. For low values of resistance and elect voltage, the load current is independent of resistance, so it's characteristic of a current source, a constant current source. At higher values of resistance, the elect voltage is the missing load current, the I radiation minus I load, which is linear, the elect voltage, as that one view graph showed us. It is characteristic of a shunt current or load conductance. The interpretation is that we have a current source due to the particulate ionizing radiation, and a shunt current due to the ionizing gas between the electrodes. Thomson and Rutherford predicted that conduction of ionized gas would be linear in voltage for low voltages, and then Thomson in 1899 derives the equation for current density. Here are the plots of spontaneous power versus resistance. This is for 80, 140, and 185 degrees C. And you see the power peaks and then goes down. You can see that at the highest temperature the power peaks higher, and it peaks at a lower ohm resistance, which is a higher load. And actually this behavior is what you would expect for some types of power supplies. This is a phenomenological equivalent circuit based on the Norton equivalent circuit representation of the processes within the cell based on our experimental data. On the far left we have a current source, which is composed of the radiation that's being produced. We have a working electrode with a work function and a counter electrode with that work function. You can see the ions are being produced, and some of them are migrating between the electrodes. You also have a shunt conductance, and that is the current that's transferred in the cell. And you have a cell capacitance. On the outside of the cell, we have a load, and it's a variable load, where we get the plus and minus as we can measure the voltages. The shunt conductance term is the phenomenological equivalent circuit represents an internal loss of spontaneous conduction from the load. In some respects, a LEC is similar to an ionization chamber with an internal source of radiation. To better understand the nature of the shunt conduction, a LEC cell can be operated as an ionization chamber by using external voltage and measuring the resulting conduction current. In order to maximize the available power to the load resistance may be adjusted to reduce the load voltage and thus reduce the shunt current. Shunt conduction can also be minimized by cell designs as well as by adjusting the load impedance. Spontaneous load to shunt power. This is an interesting plot because as we look at this, what you see is that the shunt current goes up higher than the load current at the higher load resistances. We were interested in determining what the ratio of the power going into the shunt relative to the power going to the load. Here we have for load resistance at a temperature of 185 degrees C. And what you see is the shunt current is going up, the ratio is going up, and so in effect there are, at one of our calculations, it was 17 times more power was going into the shunt power than going into the load power. Here's an Arrhenius plot of the maximum load power at temperatures from 29 degrees C to 185 degrees C, and it's versus the inverse temperature. You can see in the far right, which is about room temperature, that the slope of the line is pretty steep, and it gradually bends over to, by the time it's 80 degrees C to 185 degrees C, we got a very nice straight line. The activation energy is a function of the slope of this line, and if you calculate the activation energy between 80 degrees C and 185 degrees C, it was about 0.601 electron volts based on the current. At lower temperatures, the activation energy ranges from about 4 to 1, and the vacancies also increase with temperature. This is one of the reasons we think that vacancies are important. Some observations. The radiation current is approximately constant for measured load resistances and increases with increasing temperature. Maximum load power occurs for different load resistance as temperature increases. Maximum load power increases approximately exponentially with increasing lattice temperature, as shown by the Arrhenius curve, and the lower load resistance needed for higher temperature. The physics of the shunt current or gas ionization should be studied as an opportunity to optimize the LEC's performance. Here's one of the LEC cells that I talked about earlier. In this case, we have the PD-coated electrode in the center, and we have the counter electrodes are alternating fins of copper and zinc. This test was conducted where the glass mason jar, which is about 4 inches in diameter. The reason we wanted that was we wanted if it was particulate ionization, we wanted to be out in the Bragg curve where the bulk of the ions are produced. We had DBMs going across between a zinc fin and a copper fin. We also had a DBM going from the palladium cathode to a copper fin. Here's an example of the LEC voltages between the fins and the active electrode in the cell configured as shown in the previous slide. The temperature is Kelvin divided by 1,000, and so you see as the temperature goes up a little bit, the copper to zinc volts through a 10 megohms you can see it ranges from about 100 millivolts to 225 millivolts. At the same time, the copper to PD through a 5 megohm load was negative, starting at about minus 50 millivolts down to a little over minus 100 millivolts. And so this slide shows that it is possible to harvest some of this energy, which is the contact potential difference or volta effect. Although the work of J.J. Thomson was remarkable for its time and has been valuable in our analysis, he did not have some of the same things that we have. For example, he did not have electrodes that were emanating radiation. In our two-electrode working electrode versus counter-electrode, where we induced a conduction by applying a voltage, it does not correspond to his predictions. The Leck-induced current versus voltage did not saturate as he predicted. The measured current versus voltage is greater than predicted for radiated particles with constant velocity, and measured current versus voltage, IV, is greater than predicted for ions of all the same size. Alternative multi-electrode geometries may offer attractive Leck implementations. Some conclusions, observations, and speculations. Conclusion: something is ionizing the gas. The source of the ionized gas, we know it's the PDH or PDD lattice, but we don't know what the mechanism is. The specific ionization produced, we don't know if it's particulate or alpha, beta, something else, or electromagnetic. It's not identified. The flux of the ionization increased monotonically with increased temperature. The mechanism that produces the ionization is unknown. However, experimental evidence indicates that vacancies, including superabundant vacancies, are important. These results provide strong evidence that low energy reactions occur. They may be related to some of the documented biological transmutations that John Paul Barbarian has published several papers on, but clearly more research is needed. Approximately 4 months ago, we became aware of a paper that was published in 1996 by R.K. Rout, Dr. Srinivasan, and the team at BARC, entitled Reproducible Anomalous Emissions from Palladium Deuteride Hydride. This paper is available along with others in the LENR CANR library. In the last two paragraphs of the conclusions, the phenomena, though most easily reproducible in palladium, are perhaps more universal and may also be occurring when H2D2 is loaded into other metals. All the mechanisms known to us which might have fogged the films were considered and ruled out. Therefore, it is proposed that some new kind, unknown agency emitted from the loaded palladium is responsible for the fogging. It is felt that further study will not only give some additional insights for understanding this phenomena, but may also provide explanations for anomalous effects observed in other metal hydrogen systems. Clearly, this paper was ahead of its time. We discovered sometime a few months ago that palladium would produce ionizing radiation. In 1996, they were studying it. I would advise that everyone interested in this should go find this paper from the LENR CANR library and read it. They did a lot of work trying to identify the ionizing radiation and ultimately concluded that they didn't know what was causing the fogging. At the same time, several other labs, including work we were doing at SPAWAR, reported fogging of film, and I don't know that anyone ever identified exactly how that fogging occurred. In any event, this is something that I believe deserves further study, and I'm hopeful that with the collaboration we have with the team from ITTK, we will be able to look into this more. I'd like to thank again the organizers of the workshop, thank John Paul Barbarian for replication and review and advice, Andrew Erickson for replication, Pam and Roger Boss for multiple reviews and comment, Robert Means review and comment, Melvin Miles supplies, and of course Dr. Srinivasan for more than 30 years of leadership to the community. Thank you for your attention.